Imagine standing on a beautiful stretch of coast, gazing out across calm, blue water. Birds wheel overhead, the sun glitters on the ocean, an image as serene as any in our national parks. But beneath the surface, unseen forces can stir a wave so powerful it reshapes entire landscapes in moments. This is the power of a tsunami, a force of nature that scientists work tirelessly to understand and predict. Today, we'll dive into the fascinating world of tsunami simulations, uncovering how experts visualize these waves and how it helps protect coastal communities and preserve the stunning natural wonders we cherish. From real-life events to cutting-edge technology, join us as we explore the science behind one of nature's most dramatic phenomena. So, what exactly is a tsunami? Unlike the waves we see crashing on shore every day, a tsunami is a massive wave generated by powerful geological forces. These waves can be triggered by undersea earthquakes, volcanic eruptions, landslides, or even the impact of a large meteorite. When these forces disturb the seafloor, they displace enormous volumes of water, sending ripples racing outward at jetliner speeds. Out in the deep ocean, a tsunami wave might rise only a few feet high, making it nearly invisible against the rolling sea. But as the wave approaches shallower coastal waters, it slows down, grows taller, and builds into the towering walls of water that can devastate coastlines and natural habitats. This is why scientists emphasize understanding and predicting tsunami behavior, to safeguard human life and protect natural wonders like the delicate ecosystems along America's treasured coasts. Beneath the beauty of the ocean lies a world ruled by physics, and tsunamis are perfect examples of nature's raw energy in motion. A tsunami isn't just a surface wave. It's a whole column of water moving together from the ocean floor to the surface, carrying vast amounts of energy across thousands of miles. Out at sea, these waves can travel faster than a commercial airplane, sometimes over 500 miles per hour. But here's the catch. While they're moving that fast, the wave height is often tiny, maybe only a few feet, so ships or boats might not even notice the passing wave. The real danger comes when that same wave approaches shallower water near the coast. As the ocean floor rises, the wave slows down and the water piles up, growing into towering walls that can surge far inland. Scientists describe this using terms like wavelength, the distance between wave peaks, and amplitude, the wave's height. Understanding these factors is crucial in predicting how powerful a tsunami might become and where it could strike hardest. While tsunamis are rare compared to everyday waves, history reminds us just how devastating they can be. One of the most catastrophic events struck on December 26, 2004, when a massive undersea earthquake off the coast of Indonesia triggered a tsunami that raced across the Indian Ocean. Entire communities vanished in minutes. Over 230,000 lives were lost across more than a dozen countries. 7 years later, on March 11, 2011, the Tohoku region of Japan experienced a magnitude 9.0 earthquake, unleashing a tsunami that overwhelmed coastal towns and cities. Tsunami waves reached heights of over 130 feet in some areas, sweeping away homes, cars, and entire landscapes. Japan's disaster also triggered a nuclear crisis at the Fukushima Daiichi power plant, highlighting how a tsunami's impact can extend far beyond the shoreline. These tragedies serve as stark reminders of why tsunami simulations and early warning systems are so vital, not only to save human lives but to protect the natural wonders and coastal ecosystems we cherish. To protect lives and landscapes, scientists turn to one of the most powerful tools we have: simulation. Tsunami simulations help experts visualize how a wave might travel across the ocean, how high it could become, and which coastal areas might face the greatest danger. These simulations begin with seismic data, capturing details like the magnitude of an earthquake and the way the seafloor shifts. Scientists use bathymetry, the shape of the ocean floor, to see how waves will interact with underwater mountains, trenches, and coastlines. The models can reveal how waves bend around islands, focus energy into bays, or lose strength over gentle continental shelves. Researchers run thousands of scenarios to predict how fast a tsunami will arrive and how severe its impact might be. Some scientists even use massive wave tanks to study how water behaves when it hits obstacles like seawalls or coastal cliffs, crucial insights for designing better protections. With each new simulation, our understanding grows, making it possible to issue earlier warnings and plan safer communities along America's stunning coastlines and national park shores. Let's take a closer look at how a tsunami simulation actually works, step by step. It all starts with an earthquake under the ocean floor. In an instant, sections of the seabed shift, displacing huge volumes of water. Scientists feed data about this seafloor movement into powerful computer models, creating a virtual snapshot of how much water was pushed upward or downward. From that starting point, the simulation calculates how waves will radiate outward across the ocean. Every color you see on these simulation maps represents wave height, with warmer colors showing taller, more dangerous waves. The model also factors in how fast the wave travels and how ocean depths influence its speed. As the wave nears land, the simulation zooms in on coastlines, revealing how harbors, bays, or rugged cliffs might shape the incoming water. In some cases, narrow bays can funnel water, dramatically increasing wave height, a critical detail that helps determine evacuation zones. These visualizations aren't just fascinating, they save lives. Emergency managers use them to issue timely warnings and to plan for worst-case scenarios. By seeing the invisible forces beneath the sea, we're better prepared to protect both people and the breathtaking coastal landscapes found in places like our U.S. national parks. One of the most studied and sobering examples of tsunami modeling comes from the 2011 Tohoku tsunami in Japan. On March 11th, a magnitude 9.0 earthquake struck off Japan's northeast coast, shifting the seafloor dramatically and generating a colossal wave. Within minutes, tsunami waves were racing towards shore, some as high as 130 feet when they hit land. Scientists worldwide quickly ran simulations to understand the wave's behavior and predict how far it might reach. These models revealed how the wave focused its energy into certain bays and how coastal topography either absorbed or magnified its force. The Tohoku tsunami taught scientists valuable lessons about how quickly waves can travel, how complex coastal geography influences wave heights, and the critical importance of early warning systems. It's a powerful example of how science and simulation combine to help protect both people and the natural wonders along our shores. Tsunami simulations have come a long way, but the future promises even greater breakthroughs. Advancements in supercomputing and artificial intelligence are allowing scientists to run more detailed models faster than ever before. Instead of hours, some simulations can now deliver predictions in mere minutes, a crucial difference when every second counts. Researchers are also integrating real-time seismic and ocean sensor data directly into their models, creating dynamic forecasts that update as events unfold. This innovation could mean earlier warnings for coastal communities and more accurate maps showing which areas need to evacuate. Scientists are even exploring virtual reality tools to help emergency planners visualize how a tsunami might move through streets, harbors, and natural landscapes. The goal is simple: protect lives and preserve the spectacular natural beauty found along America's coasts and in our national parks. Tsunamis remind us that nature, while breathtakingly beautiful, can also be incredibly powerful. Thanks to cutting-edge simulations and the dedication of scientists around the world, we're better equipped than ever to understand these waves and prepare for what they might bring. By visualizing the invisible forces beneath the ocean, we help protect not only human life, but the fragile coastal ecosystems and stunning natural wonders that make places like our national parks so extraordinary. If you enjoyed exploring the science behind tsunami simulations, don't forget to like this video, subscribe for more fascinating nature and science content, and hit the bell so you never miss our next adventure. Until next time, stay safe, stay curious, and keep exploring the wonders of our incredible planet.